Hello, it's a pleasure for me to give this lecture on atom probe tomography. And just as in the introduction, I would like to show you this image. And this is the 3D reconstruction following the analysis of intermetallics. In fact, iron, aluminium intermetallics that were doped with boron. And what you are able to see, what you see here, is that you've got atomic plates. Only aluminium is represented. Iron is not represented. And what you are able to see is that the depth resolution here along this direction is very good. The depth resolution is perpendicular to the surface of the material. And so what you see here, in fact, is the segregation of boron atoms. Boron is in red. A segregation of boron along a dislocation line, And in order to support this, I have drawn here a Berger's circuit. Okay. And here, clearly, you've got 29 planes, while here you've got 28 atomic planes. So this means that you've got an extra half plane somewhere here. So you have a dislocation line here that is perpendicular to the image. So this clearly shows that boron segregates along this dislocation line. This is a Cottrell atmosphere. And this was published in Science in 1999. The second example is shown here, and in fact, what you see here is the precipitation, heterogeneous precipitation of small precipitates along grain boundaries. And these grain boundaries are here, and you've got two grain boundaries. You've got here a triple point. And what you see here is, in fact, the precipitation in a steel. So in a steel containing carbon, niobium, and nitrogen is what you see. That here you've got precipitates enriched in carbon. Here you can count them, 1, 2, 3, 4, and so forth. And these precipitates are enriched in niobium and also in nitrogen here. And here we have niobium, nitrogen added so as to enhance the contrast of precipitates. So clearly here you've got a 3D reconstruction of small volume showing the presence of nanoprecipitates along grain boundaries, and the volume is the volume size. The size is given here, 60 by 60. This is the size here. And 310 nanometers, this is here the scale along the depth. So this is the depth scale here along this direction. Here is the segregation of boron along grain boundaries in a nickel-based superalloy. And this nickel-based superalloy is in fact composed of two phases, and aluminium-enriched phase that is called the gamma prime, and this is gamma prime precipitate here. And here you've got another gamma prime precipitate on both sides of this grain boundary that is enriched in boron here. And you can see the misorientation between the first grain and the second one. Clearly here you see atomic planes. So again, this illustrates the depth resolution close to the atomic resolution. And here the misorientation between this grain and the other one. So clearly this is a grain boundary here, separating two grains with different orientation. So boron segregation along the GB grain boundary. Another illustration here is shown, and this is a 3D reconstruction of a small volume that was analyzed in a spin valve for random access memory. And this is a tunnel junction here, composed of platinum, cobalt, and oxide, aluminum oxide, Al2O3. And this reconstruction clearly shows you that you've got silicon, this is a substrate, and after you've got platinum, cobalt, the cobalt enriched layer. So here you've got the oxide that is enriched in aluminium, in pink here, enriched in oxygen also, because this is an oxide, so the oxygen is here in black. So again, after you've got platinum, cobalt, aluminium, and oxygen. So clearly this shows you the stacking sequence of this spin valve, platinum, cobalt, oxide, platinum, cobalt, oxide, and so forth. So the summary, the outline of my talk is shown here. So I will first explain to you how we can generate a high electric field. This is the basics of atom probe and also of field line microscopy. Here you've got the field line micrography and showing you with a tip, because we will produce a high field with a tip. And after I will discuss the history of field line microscopy and atom probe tomography. And after we'll discuss the fundamentals of field line microscopy, physics of field evaporation. I will describe the basic principles of atom probe tomography here, and I will discuss mass resolution, spatial resolution, quantitativity, statistics. And through all this presentation, I will illustrate what we can do with atom probe tomography in material science, including metallurgy, nanosciences, nanoelectronics. So, how to generate high electric field? So, consider that you've got a tip, so you will be able to produce a high electric field simply using a tip with a very small radius, tip radius. And this will be the specimens that you observe by field line microscopy and that you analyze. So you have to elaborate the specimens that you want to analyze in the form of a sharply pointed needle. So coming back to the basics of electrostatics and how to generate high electric field. So I just recall the Maxwell equations so that you can produce a high electric field, simply by having electric charge at the surface of an object. Here this will be a sphere in the first approach, divided by the permittivity. And this field is also equal to the gradient of the electric voltage, and there is of course a minus here. And so if you've got a sphere here, simply the voltage, the electric potential is equal to Q, the electric charge, divided by this factor that is proportional to the tip radius. Okay? And so the field that is the gradient of V simply is Q divided by these factors. That is times proportional to the squared function of the tip radius. So that means that the field is proportional, is equal for a sphere to V divided by R. Okay? So this is for a charged sphere. But now if you consider a sharp tip, this will be close to that, but you have here a correction factor, beta. This is the field factor. Simply, at the apex of this tip, you haven't got a sphere, you've got a truncated cone terminated by an hemisphere, not really an hemisphere, but a curved surface here. So you can write that the field in the first approach is equal to the applied voltage divided by beta R, with beta is a factor, the field factor that depends on the shape of the tip and the electrostatic environment inside the instrument. For instance, if you take a tip radius of 50 nanometers and the voltage that is applied equal to 10 kilovolt, then the field produced will be close to 40 volt per nanometer. So this is a very large high electric field. If this applied voltage here is negative, so you will have repulse electrons, so you will have field emission of electrons. So we won't talk about this technique. That is called FEM for field emission microscopy. Instead, in the field line microscope, in the atom probe, the two instruments that we will discuss, for V positive, you will have two phenomena that are exploited. First, this high voltage, positive voltage, will produce field ionization of a rare gas. If you introduce a gas in the analysis chamber, you will have this ionization, and using this process, you will be able to produce an image. And this is field line microscopy. If you now increase a little bit more the applied voltage, so you will be able to field evaporate surface atoms. So this is the atoms of this specimen. Previously, it was not the atoms of the specimen, it was simply the rare gas. This rare gas can be helium, neon, or argon. Okay? So, two phenomena, very different. Okay? So coming back to the history of atom probe tomography, and so we have to come back to 1926. And what was the context at this time was quantum mechanics emergence and the discovery of Thunel effect for electrons. And this was in fact the starting point for the thesis of Erwin Müller. Erwin Müller is the inventor of field line microscopy, but also of field emission of electrons for V negative. And in 51, so instead of applying a negative voltage, Müller applied a positive voltage. So he invented the field line microscope in the 50s, and with this microscope, the atomic resolution was reached for the first time, and this was attained for a temperature of the tip, temperature of the specimen, less than 80 Kelvin, so that to decrease the thermal excitation. Okay, and afterwards, the brightness of images was improved using macro channel plates, which is an amplifier, an electron amplifier. Okay. MCP, micro channel plates. 67, this is the invention of the atom probe by Erwin Müller. This at the time was not a tomographic atom probe, was not a 3D atom probe, this was what we could call a one-dimensional atom probe. And the basics and the principle is based on time of flight mass spectrometry of atoms that are evaporated from the tip surface. So 73, this is the imaging atom probe proposed by John Panitz. 79, the laser atom probe developed by Kellogg and Tsong. Tsong is a student, as well as Kellogg, of Müller in NV80, and this is the starting point, the beginning of the applications of atom probe, of one-dimensional atom probe in physical metallurgy for steels, superalloys, and so forth. 88. So clearly there is a revolution, because in 8 years it is the invention of the first 3D atom probe by Alfred Cerezo and George Smith at Oxford. And this is the invention of the position-sensitive atom probe. This is the POSAP. This instrument was commercialized afterwards by the company, the Kinsbrisk. 1989, a second design of atom probe, of 3D atom probe, was proposed by Alain Bostel, Didier Blavette, and Alain Monin in 1989. This was shown at the IFES meeting of Oxford, so in 1989. 1992, a third type of 3D atom probe was proposed by Mike Miller, but in fact this optical atom probe, which was the name of this type of 3D atom probe, was never really used in fact. 93, this is the first applications of the tomographic atom probe presented in 89. This is the TAP, tomographic atom probe, and the first results were published in 93. 1996, Cameca was involved in the commercialization of this new instrument with the French group, with the GPM. And in the 90s, there was also very interesting researchers conducted by the Oxford group. And in fact, they use a nanosecond laser atom probe to investigate semiconductors. As an example, indium phosphorus quantum wells. And this was done with the position-sensitive atom probe, the POSAP. So in 1988, we've got a very important step with the development of a new type of 3D atom probe. This is the local electrode atom probe, and this was introduced by Tom Kelly at Madison, and finally commercialized by Imago, the company Imago, for the commercialization of the LIP technology. In the 90s, we have also a very important step for the preparation of tips instead of electropolishing. So Mike Miller and Larson proposed to use focused ion beam to ion mill the tip. And this was very important, in particular for nanosciences, because we could prepare a tip with multi-layers, for instance, here you've got, and afterwards, this is a team image, and here you have a 3D reconstruction of these multi-layers. In 2004, so the French group developed the first laser tomographic atom probe using femtosecond laser process. And shortly after, the laser LIP was developed by Imago and commercialized. Okay, and the commercialization, of course, of the French laser-assisted atom probe, this commercialization was launched at the same time by Cameca. And finally, the end of this history of the two companies, Cameca and Imago, and the end of the first page of the history is in 2010 with this important event. Finally, Imago joins Cameca. Let us introduce the principle of field-line microscope. So this was, in fact, the first atomic resolution microscope, and Erwin Muller was the inventor, and this was in the 50s. So you can see here Erwin Muller with the first field-line microscope. This was a glass microscope here, and behind you've got a ball model of a chip. So you can see here the first layer, the second plane, the third plane, and so forth. And so imagine that you got a tip like this. These are atoms. And so you applied a high voltage, let's say 10 kilovolt, and the tip radius is 50 nanometers, so you will be able to produce an electric field close to 40 volts per nanometer. And with this high electric field, you will be able to ionize a gas atom, a gas composed of, for instance, helium, neon, or argon. So you place this tip in a vacuum chamber. This is the analysis chamber, okay? And so you will introduce neon, for instance. That is a rare gas. And this gas will be ionized preferentially close to the tip. And more precisely, close to the atoms that are that are protuberant here. So this means that you will be able to ionize these gas atoms close to the edges, these edges of the first plane, or the second layer, or the third one. So that means that you will have a preferential field ionization of gas atoms close to the layer edges here. Here, for the second layer, the third one is here, and so forth. So you will be able to form an image of the field distribution. Why? Because these gas atoms will be positive ions, and so these ions will be repelled by the tip that is positively biased. And so these ions will be repelled from the tip up to a screen, and the screen is phosphorus with an amplifier composed of a microchannel plate. I cannot come into details about that. And so you will form on this screen an image, a magnified image of the distribution of the electric field, so of the distribution of atoms at the tip surface, in particular of atoms that are in protuberance at the tip surface. So you can have a very atomic resolution with this instrument, with field line microscopy, if you got low temperature, below 80 Kelvin typically, in order to get a good spatial resolution. Atomic resolution is only obtained at low temperature, and so that to minimize thermal problems, agitation. And so this is also the typical pressure that is used, 10 to the minus 5 torque. This is partial pressure of neon, for instance, or helium and argon. So let us keep in mind that you will have an image that is in fact a magnified image of the distribution of atoms at the tip surface, and the magnification is proportional to the ratio of this distance between the screen and the tip divided by the tip radius. This is close to a stereographic projection. So all the trajectories seem to come from a single point that is somewhere here, and so you've got trajectories like this, all coming from a single point. This is the projection point. Okay. So, as I said, with this field line microscope, you will be able to get an image of protuberant atoms. So if you come back, if you keep in mind the ball model, here you've got the first layer, the second one that I showed you previously, the third one. Okay, and this is in fact, an image showing the O1 pole of platinum here, and here you are able to see individual atoms. So the magnification is typically 1,000,000. So you've got a very high magnification, a very large magnification. And also the atomic resolution is reached here. Each dot here is the image of a single atom here. You notice also that you've got symmetries. Okay, so you are able to see, for instance, the 1, 1, 3 poles here, and you've got here symmetries around O1, showing so the symmetry of the crystal. Now this is another example, and here we try to get an image of an alloy composed of aluminium and copper. So aluminium and copper. And what you are able to see here is that you have got not only poles, and in fact you see that you have a lower resolution than previously. The atomic resolution is not really rich here, but you are able to see that you've got here bright lines, bright platelets here. Again, ici. This is precipitates, and these precipitates are in fact Guinea-Preston zones, GP zones. This is copper enriched precipitates that form in this material. So this means that with phenol microscopy, you are able to see the microstructure of a material like here, aluminium copper, and to see precipitates in bright contrast, while the matrix here is darkly imaged. So after field ionization, we've got a very important phenomenon that is exploited in atom probe. This is field evaporation of surface atoms. So if you increase the electric field by increasing the apply voltage, if you increase this field up to a threshold that is called the evaporation field, so you will assist to field evaporation. And with this new process, this phenomena, so you will be able to evaporate surface atoms in the form of ions, and then these ions can be identified by time-of-flight mass spectrometry. And so we are able to identify atoms that are observed by field microscopy simply by time-of-flight mass spectrometry. This is the principle of one-dimensional atom probe. And so you can analyze the chip layer by layer, and in the 3D atom probe, the atom probe tomograph, so you will be able to have a 3D reconstruction of the analyzed volume with both the identification of atoms by time-of-flight mass spectrometry, but also you will be able to localize, to find the position of atoms in the 3 dimensions of the analyzed volume. And this is an image here showing a field micrograph of tungsten. So here you can see individual atoms of the first layer, the second layer, the third layer. This is a low index plane, pole. You can see symmetries here. And so you will evaporate this tip from the edge here, the edges of planes, because here you've got the highest electric field. So now let us come back to the fundamentals, the principles of field evaporation. And what we have plotted here is this is the potential energy of atoms or ions as a function of distance from the tip surface. This is the surface, and here the distance. This is the x axis. So the first step is, what about the activation energy for the evaporation of a surface atom without any electric field? And this activation energy, Q0, is in fact the sum of what? The sublimation energy, lambda, the ionization energies, this is this term here, and the work functions, and this is the third term here. Okay, and there is a negative here term because of course we get back the energy because of the electrons coming back to the tip. And now if we've got an electric field, and so this activation energy will be smaller and will be reduced in the presence of this electric field. And in fact, in the first approach, we can write that Q is Q0 minus Ke, with E the electric field. So in white here, I have plot the first term, Q0, for as a function of the distance here. And in the presence of an electric field, you can see that this curve, this white curve, is changed into the black one. And so the barrier is smaller. This is Q of E here. So clearly, when you've got an electric field, so the barrier for atoms, for surface atoms, to field evaporate in the form of ions is reduced. So now let us coming back to this expression. So clearly, this activation energy can be null. If you write Q of E is equal to 0, you will have an electric field threshold, ES, that is defined by this expression equal to 0. And if you write this, then you can substitute K in expression as a function of ES, and so you will be able to write that Q of E, the electric field, is equal to Q0 multiplied by this factor. So clearly, ES is the threshold, this is the evaporation field for which you've got Q of E is equal to 0. Now, if you try to write the evaporation rate, so this evaporation rate is proportional to this Boltzmann factor, depending on this barrier, 8, Q of E. And so you can see that when you have an electric field E equal to the threshold, the evaporation field, so Q of E is equal to 0, so here phi is equal to phi 0. So that means that phi 0 here is the evaporation rate when you've got an electric field equal to the evaporation field. Now coming back to finite microscopy, I showed you previously that you had GP zones that were brightly imaged. Why these precipitates are brightly imaged? This is here another example where you have a nickel-based superalloy in which you've got gamma prime precipitate, and these gamma prime precipitates are aluminum enriched. And these precipitates appear in bright. Okay, so you've got large precipitates here, and also small ones that here. This is an image coming from Oxford. This was the work of Bevan. Okay. So why it is brightly imaged? In fact, precipitates appear in bright contrast because they have a higher evaporation field. In fact, in a two-phase material, the two phases generally have different evaporation field. And here precipitates have a higher evaporation field, leading to a higher ionization rate of emerging gas. So this is the reasons. you've got this contrast. And this contrast is important because you will be able to localize, to have a picture announcing and exhibiting the presence of precipitates. Now let us describe briefly the principle of atom probe tomography. So again, we've got a tip, and if we apply a positive voltage on this tip, again we will have an electric field. Okay. Now imagine that you've got 5 kilovolts applying to this tip. And so the electric field that is applied is not sufficient to fill evaporate surface atoms. That means that atoms are stable at the tip surface. And this tip is in vacuum, okay? You have no emerging gas. This is not field line microscopy. You are in vacuum, typically 10 to minus 9, 10 to minus 10 torr, okay? And so the atoms here are stable. Now, if you superimpose high voltage pulses to this DC voltage, and if this pulse is sufficient, let's say 1 kilovolt, to reach the electric field that is necessary, that is required to field evaporate, so you will have field evaporation of surface atoms up to the detector, okay? If you are able to detect the time here to the detector, as you know what is the starting time, so you are able to calculate the time of flight, to know the time of flight. If you know the time of flight, then you know the velocity, because it's simply the distance between the tip and the screen and the detector divided by the time of flight. And so you know the velocity. If you simply write the conservation of the energy, initially, what is the energy? It's essentially electrostatic energy, and this electrostatic energy is equal to the kinetics energy. So from this equation, you can simply deduce that the mass to charge ratio, n is the ionization number, n is equal to 1 means 1 plus ion, and equal to 2 plus ion. So you can deduce from this equation that m over n is equal to this expression. So clearly, if you are able to measure the time of flight, you are able to calculate the mass to charge ratio, and then you are able to identify the nature, the chemical nature of surface atoms. For instance, you will find for aluminium 27 atomic mass unit if the charge state is 1. If it is n equal to 2, you will have 13.5 atomic mass unit. Okay? So this is, in fact, the electric mode. We superimposed electric pulses to a DC voltage. Okay. But if we want now analyze not only metallic alloys, but materials that are not good conductors, that are poor conductors of electricity, so we will replace electric pulses by laser pulses. This was introduced initially by Kellogg. And so let's imagine that you've got 5 kilovolts again on this sample, on this tip. Atoms are stable, there is no evaporation. And with these laser pulses, so you will increase the temperature of the specimen at the surface. And so you will be able to field evaporate surface atom by thermal activations. So again, so this surface atom will be repulsed, repelled by the tip, and then you will have an ion impact on the detector. So clearly you can have two modes: high voltage pulses for metals and laser pulses for insulator or semiconductors Okay, but in both cases you haven't got only one, of course, pulse, but you've got let's say 100,000 pulses per second. So the repetition rate is 100 kilohertz. Okay, and for each pulse you measure the time of light. Okay, and in fact for each pulse you evaporate a very small amount of atoms. In average, you will have, let's say, something like 0.01 ion per pulse for the detection rate. Okay, this is very small detection rate, and this is necessary, this is required, so that to have a quantitative analysis, because if you've got too much ions, too much ion impacts on this detector, so you will have problems because the detector will not be able to measure properly the time of flight. So typically, this is a mass spectrum of semiconductor, indium, containing indium, aluminium, gallium, nitrogen. And so here what we have is the number of ions that we detected as a function of the mass to charge ratio, M, and N is the ionization state, N equal 1, 2, 3 if this is a 3 plus ion. Okay, so clearly in this mass spectrum you can identify all the chemical species. For instance, here aluminium 2 plus is at 13.5 because the mass of aluminum is 27. 27 divided by 2 is equal to 13.5. You can have also a peak here. If this is the N2, so N is the mass of nitrogen is 14 atomic mass units, so N2, 28. So this peak is at 28, and so forth. So you've got gallium also, indium. Okay, and so you can see in this zoom here that you got indium, but you've got a background noise here. So this is important for the quantitativity, of the instrument. How we can reconstruct the images? So again, you've got the tip here, the ion impact is here. And now we will make the assumption that the atom probe is a point projection microscope. What does that mean? That we can approximate all the trajectories as lines, like this, straight lines, and all the trajectories come from a single point that is called the projection point here. And this point here is located a little bit behind the center of the sphere, of the hemisphere here. Okay, and if this is if the atom probe, the 3D atom probe, is a point projection microscope, so we can say that magnification is equal to the ratio between the flight path, the length of the flight path, divided by the tip radius, multiplied by a factor here that is the image compression factor plus 1. Okay. So if you had a strict stereographic projection, so M would be equal to 1. But instead of that, generally M is not exactly equal to 1. It can be equal to 0.7, 0.8, 0.6. Okay. So if you calculate the magnification, you will find something like 10 to the 6. If you take for L 10 centimeters and R is equal to, let's say, 50 nanometers, so we'll find magnification of 1,000,000. Okay. So if you know the magnification, if you know what are the coordinates of the ion impacts, So you will be able to calculate the coordinates of the surface atoms at the tip surface. Okay? So here you can see the magnification depends on the tip radius, but with tip radius you can calculate it if you know what is the applied voltage and if you know what is the evaporation field here. So this is the same equation as previously described. And the analyzed area can be calculated also. This is simply the ratio between the size of the detector divided by the magnification. So here G is the same as M. Okay? And so you can have something close to 100 nanometers. So now, how can you generate the depth scale? So the depth scale is what? It's simply proportional to the number of layers that you feel evaporate. So it is proportional, the depth is proportional to the cumulative number of ions that you detect, okay? So this is simply written here. So if you count the number of ions, you know what is the atomic volume of each atom, of atoms in this material. So you can calculate the depth scale using let us illustrate what we can do with atom probe tomography. In particular here, this is a 3D reconstruction of nickel-based superalloys that is a two-phase material composed of a matrix that is enriched in chromium. Chromium is here in green. And the precipitates are enriched in aluminium, and these precipitates are shown here in yellow contrast. This is simply envelopes. This is iso concentration surfaces in order to enhance the position of precipitates in this material. So you can see several precipitates here that are enriched in aluminium. And one thing that is important to see here, this is the depth direction here, perpendicular to the tip surface. And typically here you've got 10 nanometers. So the surface that is analyzed is, let's say, 20 nanometers here. And if you look at this zoom, you are able to see that these precipitates here, in this precipitate, you can see atomic planes. So again, you can see that the depth resolution is very good and is close to the atomic resolution. And you can see here in red, aluminium enriched planes that alternate with plates that contains no aluminium. So this is really the signature of long-range orders that exist in these small precipitates. And the size of these precipitates, you can count the number of planes, and the lattice parameter being close to 0.35 nanometers. So you've got 20 atomic planes here. So that means that the size of this precipitate is close to 7 nanometers. In this slide, I would like to illustrate the ultimate depth resolution of atom probe tomography and its importance for the investigation of long-range order. So if you come back to the gamma prime phase in nickel-based superalloys, it was the previous example. Gamma prime phase, an ordered structure, a nice L, which is the L12 ordered structure, and this structure is as follows. You've got aluminium in red here, and nickel in gray. And so clearly, if you investigate this phase along the 001 direction, so you will have mixed planes containing both aluminium and nickel in gray, with nickel enriched planes composed of only nickel if it is a binary system with only nickel and aluminium. And again, you've got a mixed plane containing aluminium with a concentration close to 50%. So clearly, the L1 phase can be described by a static concentration wave that shows a mixed plane, aluminum enriched planes, with nickel enriched planes, aluminum enriched plane, and so forth. And this is illustrated in these concentration profiles, in which you've got the alternation of aluminum here, of aluminum enriched planes with nickel depleted layers. And you've got here an aluminum depleted plane that is enriched in nickel. And the concentration of nickel is 100% in good agreement with the stacking sequence that is weighted. And the concentration of aluminum in this nickel enriched layers is close to 0. And if you look now to the addition elements, tantalum, tungsten, and titanium, you can see that tantalum is preferentially located in aluminum enriched planes. This means that tantalum, probably this suggests that tantalum substitutes for aluminum in this ordered structure. So tantalum is probably here in this substitute for aluminum in these sides here, in the corner sides. In contrast to the center of phases, phase center. Okay, and this is also the case of titanium. Titanium is preferentially located in the aluminum enriched planes, suggesting that titanium substitutes for aluminum in this ordered structure, the L12 Ni3Al ordered structure. If we now use laser pulses, so we will be able to analyze semiconductors, and this opens very good, very interesting perspectives for the investigation of transistor, of MOSFET transistor, and investigation of microelectronics in a more general way. And so we can use laser-assisted chromatography for the study of 3D distribution of dopants, boron, phosphorus, arsenic in materials. This is an example of what we can do. This is a tip as observed by transmission electron microscopy. Okay, and what you are able to see is a MOSFET transistor here. This is the source here, or the drain. Here you've got the gate, and here this is the 3D reconstruction using atom probe tomography. Okay, so this is the team image, and afterwards we put this tip in the tomographic atom probe in the instrument, and we analyzed this material, and we reconstructed the distribution of silicon atoms. And what you see here, you are able to see the distribution of boron, boron atom. Boron, so is a dopant, okay? And what you see here is that boron is preferentially located here, in this region, close to the source, and here you've got also boron in the gate region. So I don't want to come into the detail, but I simply want to show you that you can make correlative investigation using both TEAM, transmission electron microscopy, and atom probe tomography. This is another example of what we can do with atom probe tomography. This is a picture, a map of the distribution of dopants in an N-MOSFET structure. And what you are able to see here is that here you've got here the gate. These are the source and drain regions. Here, this is clearly the evidence that you've got phosphorus in the gate. And here, this is an oxide that is here, and this is the gate oxide here, and this is here the substrate of the MOSFET transistor. Now we will discuss briefly the problem of the quantitativity of composition measurement. So clearly this quantitativity depends on mass resolution and background noise, but also on some problems that we have. And these problems are the preferential evaporation of atoms to the DC field and the problems related to the detection of ions. So first, mass resolution and the background noise. So clearly, the identification of chemical species in mass spectra is, of course, easier when you've got well-resolved peaks, in other terms, if the mass resolution is good. So that to avoid or to minimize overlaps between neighbor peaks. So consequently, the analysis will be better and the quantitative will be higher if you've got a high mass resolution. Also, you should have a low background noise so that to get the best sensitivity, of course, and reliability of composition measurement. Reliability, of course, will be larger if you got low background noise. I would like here to introduce the concept of local electrode atom probe, LEAP. And what is the principle? So you've got a local electrode and you apply negative pulses on this electrode instead of positive pulses on tips. And so this local electrode is very close to the tip that you want to analyze. In fact, a few tenths micron far from the tip. The diameter of the local electrode is typically 50 microns in diameter. And so this concept was introduced first by Penitz and after by Nishikawa. This was in the 90s, the scanning atom probe. And this was developed afterwards by Tom Kelly. And this is the principle of the local electrode atom probe. So there is many advantages of using a local electrodes. First, you can select a given tip here, and you can have an array of tips on a specimen holder. And so you can analyze a selected tip among several specimens placed on the surface. Also, with local electrodes, you can have a larger mass resolution because with that you can, with local electrode, you can have a smaller pulse, 8. And so the resolution, the mass resolution is better. So you've got smaller energy deficits. And also with local electrode, you can have higher pulse repetition rates because it's easier to get higher pulse repetition with local electrode because the voltage that is applied on the local electrode is smaller. So the second source of problems, if you want to have a good quantitativity, is the problem of preferential evaporation to DC field. More precisely, this is the problem of the preferential evaporation of low evaporation field atoms to the DC field. So let us consider A-B alloy, where B atoms have a lower evaporation field. And let us keep constant the total electric field. So I mean the total electric field is related to the total voltage applied to the pulse, to the tip. So this is the DC voltage plus the pulses, the pulse voltage. So this is constant. Okay, so this means that the evaporation rate is constant. So what is the problem? If the DC field is too high, I mean the DC voltage. So that means that you will have a too low pulse fraction. Of course, the pulse height will be smaller if you've got a VDC that is larger. In this case, you can have preferential evaporation of low evaporation field B atoms here in red. Okay, so of course all the B atoms will not be preferentially evaporated at the DC voltage, but part of them. So that means that you will have an underestimation of the amount of B atoms. That means that the atomic fraction of B atoms that you measure is smaller than expected. So this means that to get quantitative composition, one should decrease the DC field. So we have to decrease the DC voltage. So that means that we have to increase the pulse fraction. Okay, so typically 20%. And so we have to have a high pulse fraction so that to have quantitative data with respect to the problem of preferential evaporation. This is true for the electric mode, but also for the laser mode, because in the laser mode, instead of having an electric pulse, we've got a laser pulse, a light pulse. And so if we want quantitative data, so we have to have a low VDC. So this means that we should have a large laser pulse. So in order to get quantitative data, we should use sufficient high laser pulse that is relatively high. The third source of problems related to quantitativity is the problem of the detection of ions. And here you've got here the schematic picture of the atom probe, of a tomographic atom probe. So you've got the tip, and here the detection system is composed of a channel plates here. This is simply an amplifier of charges, because here you've got a very small charge. It is equivalent to 1 electron or 2 or 3 electrons, depending on the ionization state, 1, 2, 3. And after this channel plate, you've got, let's say, 10 to the 5th electrons generated by these channel plates. And these electrons strike here a detection that is based on deadly lines. Of course, because the open area of channel plates is not 100%, you haven't got detector efficiency equal to 100%, but instead 50%. So 50% is the open area of these channel plates. This detector, in fact, is based on the use of daily lines. There is 2 daily lines. One is along the x-axis. So this is the here this line here, and the second one is for the y position. This is in green here. In green, if you want the x position along this direction, so this is shown here, and you can see that the x position is simply proportional to the difference between t left and t right. In the same way, y is proportional to the difference between t down and t up. So this is the principle of daily line detectors, DLD. So using this type of detector, you will have problems if you've got too much ions coming and striking the detector at the same time or close, and in the close vicinity of each other. Multi-hit, time of flight events close to each other in space and time may overlap and can be interpreted as a single event. So of course you will have a problem of quantitativity if you count only one impact instead of 2. And so this leads to an underestimation of species that are more prone to multi-events, and these are not necessarily the major components. And of course, you can have correlated feed evaporation of neighbor atoms at the tip surface, and so you can have more pronounced fire effects on the detector. And this will lead to severe bias in composition data. Okay, so for a given technology, so you should use a very low detection rate, typically less than 0.01 ion particles. So let's go now to the problem of statistics for the measurement of composition. So if you've got an atomic fraction of B atoms, CB, this is simply equal to the ratio of NB over the total number of atoms in the binary atom. Okay? And so if you want to know what is the precision is in fact controlled by the by sigma. This is the standard deviation, and this is the square root of this expression. Okay, and the sampling errors, so due to statistics, is simply equal to 2 times the standard deviation here. So now let us consider the spatial resolution, and we have to consider 2 components: the in-depth resolution and the lateral resolution. The depth resolution is typically 0.1 nanometer, and this is controlled by the screening of the electric field here. For instance, we show here an image, a reconstruction, where you can see the 110 planes in tungsten. So clearly, along the depth scale, you've got a resolution close to the atomic scale. In contrast, when you consider the lateral resolution, I mean the resolution parallel to the surface, to the tip surface, this resolution is limited by the aberration of ion trajectories that occur near the tip surface. You've got aberrations, so you've got simply a point projection, but it is more complicated than this because of the topology of the tip surface. Okay, so you've got aberrations. So the model that we used before, the simple projection, is not really exact. And these aberrations lead to imprecision at the tip surface. That means that we will not be able to reconstruct the material at the atomic scale in the 3 directions. The atomic scale is only reached along the tip axis. I mean, perpendicular to the tip surface. So now we've understood that the lateral resolution parallel to the surface is not as good as the depth resolution. And this is because of the trajectory aberrations. So in pure metals, so in one-phase material, in fact, the resolution, the spatial resolution, is typically, let's say, 0.5 nanometers. But the situation in 2-phase materials is much worse. In fact, let us consider that you've got a small precipitate. So this is a low evaporation field region. Okay, and this leads to focusing effects. In contrast, when you've got a high evaporation field region, a precipitate that has a high evaporation field, so you've got defocusing effects. So clearly the trajectories are influenced by the local electric field and of course, of the local curvature. Yeah. So this leads to problems and bias in the composition measurement. So you will have problems with the reconstruction, of course, because the reconstruction is not a simple point projection as previously said, but it is more complicated, of course, because of the topology of the tip surface that is not simply a spherical cap, but you've got local curvatures here leading to defocusing or focusing effects. So this is the first influence, the first effect is that your reconstructions will not be accurate. But the second consequence is that you will have bias in composition data for, in particular, for small precipitates. And the reason for that is that you can have solvent atoms coming from the surrounding matrix. These atoms can fall in the precipitate region that is enriched in B, and this will lead to another estimation of solvent atoms. And the consequence is that you will have, of course, an atomic fraction of A atoms that will be larger than expected. So a lower atomic fraction of B atoms, of course, in the precipitate. Here I have shown an example of NBC precipitate. This is small carbides in a steel, and these precipitates are carbides, and they have a higher evaporation field, and so the curvature here, the radius is smaller than the tip radius, so you get a protuberance. This will lead to a defocusing effect, and so you will have problems in the measurement of composition. This is an example of here showing this effect for field-line macroscopy. This is a field-line macroscopy. As a conclusion, this is a summary of important points here. So clearly, atom probe tomography makes it possible 3D imaging of chemical species at the 8-bit scale. The resolution is very good, perpendicular to the surface. This is the depth resolution. In contrast, the surface, the lateral resolution parallel to the surface of the tip is much worse, in particular for two-phase materials. This is a destructive approach because, of course, you field evaporate, and layer by layer, the specimen is destroyed, and so you cannot make twice the same experiment. This technique can not only analyze and investigate metals in the electric mode, but if you use laser pulses, you can investigate semiconductors as well as insulator, oxides, and so forth. So this is the typical analyzed volume. So this means this is rather small. So that means that if you want to, for instance, to investigate band boundary, you have to use correlative approaches, in particular, in combination with a transmission electron microscopy in order to locate the grand boundary and then to extract the region of interest using focused ion beam ion milling. If you take care, you can have quantitative measurements of composition, particularly if you take care to the problem of mass resolution and the proper identification of peaks in the mass spectrum. You should also take into account the problem of preferential evaporation and also the issues related to detection of ions, and use for that low detection rate. So as already said, there is problems with local magnification effects, and these affect the lateral resolution and quantitativity, both for the reconstruction of image, but also for the composition measurement. The sensitivity is between 5 and 100 ppm, depending on the material, but also on the instrumental conditions. One strong point of atom probe tomography is that you've got equal sensitivity to every element in principle. And you can detect from hydrogen, boron, carbon, nitrogen, up to refractory elements. So, thank you for your attention.